Check it out now, y'all.
NanoHub U, online instruction.
Well, this lecture is going to discuss a particular system with 6 particles, and we're going to try to illustrate a lot of the essential features that need to be taken into account in order to do the statistics of this system in a meaningful way. We're really gonna get into the insides of the system. We're gonna look at all the possible states that can exist for different configurations, and in the end, I hope this example will give you a better understanding of the formalism that we're basically going to derive in the next lecture. So this is a detailed example, and it's intended to provide you with a better understanding of the statistics of particles when they're confined into a small system. So to begin with, what is the system that we're going to discuss? The system we're going to discuss is going to have 6 distinguishable particles. These particles are going to be confined in some sort of a box, and we're going to assume that the energy levels of these particles, when they're confined to this box, are equally spaced in increments of epsilon. So the possible energy levels are going to be 0 epsilon, 1 epsilon, 2 epsilon, right? That's what I've indicated here. And furthermore, we're going to slowly increase the total energy of the particles. So we're going to say that of these 6 particles, there's a total energy E total that's distributed equally among them. And we're going to ask, what are the possible states of the system that can result? So the notation we're going to use is we're going to say that small n, and we're going to subscript n with a number. The number we subscript it with is going to be the energy state. So if we're saying that if we're thinking about, let's say, the first energy state, epsilon 1, and we have n1 particles in that energy state, that's going to be the notation that we're going to use. And we have a constraint that if we sum up all these n sub i's over all the possible states R of the system, we have to have 6 particles in the system, because that's what we started with to begin with. So that's the system. That defines the system. And what I hope to show you is that by carefully sifting through all the possible energy states, you can start to calculate probabilities that particles will be in the different energy levels. And that's, of course, what we're interested in when we're doing many particle systems. We're trying to understand how those particles are distributed in energy. So here's just another way of saying what I've already said. We can color the individual particles because they're distinguishable. We've got a system with equally spaced energy levels, and we're going to ask, as we increase the energy that's distributed among these particles, we're going to ask, what are the possible states for this particular system? So there's a few things to begin with. All the states at a given energy we're going to assume are equally accessible. We're going to say that there's no information is given about the probability of occupying a given state ahead of time up front. This is something that we're going to have to calculate. We're not going to, our initial discussion is not going to concern ourselves about which level is the most likely level for a particle to be observed experimentally. It should be clear that because the particles are distinguishable, then we expect Maxwell-Boltzmann statistics should apply, and that just simply means that the ratio of the number of particles in, let's say, energy level A compared to energy level B is going to be the ratio of the degeneracy of those 2 energy levels times e to the minus exponential of the energy difference divided by k Boltzmann T. The problem is in this discussion, we're really not going to specify the temperature T up front. And I'll try to indicate that as we go along. That'll happen in the next lecture where we explicitly put in the temperature T. So the first question is, how many states are there as the energy of the system increases? And so to try to walk you through this problem, I've constructed a table. And the table attempts to list all the different microstates that are possible for different total energies, E, capital E. So, for instance, if I say that the total energy of the system is 0, right, that means that all the particles have to be in my lowest energy state, which has an energy of 0. So I indicate that here. I've got 6 particles in the 0 energy level. And the degeneracy, the number of ways I can arrange 6 particles in one energy level when all the particles are distinguishable, right, is 1. So that microstate has a degeneracy or a weight of unity. If I increase the energy of the particles, right, so now let's say I say, okay, all the energy in the 6 particles can be equal to 1 epsilon, right? Then how do I achieve that state? Well, I would have to have 5 particles in the 0 energy state, 1 particle in the 1 energy state, and since each of these particles are distinguishable, there's 6 separate states I can have, which have 5 particles in the 0 energy state, 1 particle in the 1 energy state. And so the degeneracy of this particular state would be 6, right? And I can continue to do this as I increase the energy of the system. Here's the case when the total energy of the system is 2. There's a number of different ways I can get a total energy of the system to be equal to 2. One way is I can have 1 particle in the 2 energy level, or I could have 2 particles in the 1 energy level. Each of these different microstates has a different degeneracy, and what I find is that for this particular state with a total energy of 2 epsilon, there's 21 different ways I can achieve that particular state. So I work out the first few cases. As you can see, this case here is for a total energy in the system of 5 epsilon. When I look at the number of ways I can achieve a total energy of 5 epsilon with 6 particles, there's a number of different states that I can write down, right? Those states are listed here. If you add up the total energy of all the particles in all the states, right, you'll end up with 5. That's a constant through this whole block of the table. And over here, I list the degeneracy of each state, right? This is the number of ways that I can achieve a total energy of 5 epsilon if I've got 6 particles somehow distributed in these energy levels. So for this particular energy state, it turns out there's 252 different ways that I can achieve this total energy of 5 epsilon. And when I measure, when I reach in and do a measurement and measure the total energy of the system, and when I get the answer to 5 epsilon, right, that just tells me that I've measured 1 out of these 252 possible different states, right? So that's what this table is trying to represent. You can plot the total number of states available, right, versus the energy level. Okay, I did it up to 5. On the previous slide, I did up to 5 energy, total energy of 5 epsilon, which has a degeneracy of 252, right? I also discussed the case for 2 epsilon, which has a degeneracy of 21. Here I've extended the table out to total energy for the system of 9 epsilon, which turns out has 2002 states, right? And what you can see is that as the total energy of the system increases, the number of ways that you can achieve that total energy by rearranging these particles in those given energy levels, it goes up. It actually goes up roughly as the cube of the energy for this particular system. Once you know the total energy states available in the system, you can actually take a derivative, and you can then get this thing called the density of states, because the density of states is basically telling you how many states are available if I specify a certain region of energy. So the density of states is defined as the number of states divided by the derivative of the number of states with respect to energy. This is a concept that was first introduced in lecture 5.02. We're coming back now to reinforce it. And what I do is I just take the derivative of these discrete number of data points, and I get a curve that looks like this these red dots. You can do a least squares fit. You can show that it's approximately fit by a quadratic equation. And basically what this curve is telling you is it's telling you that if you specify some energy E, and you specify a range of energies about E, let's call it delta E, then by reading off the density of states, the dNdE at that particular energy, and multiplying by the energy with delta E, that basically tells you how many states are available in the system at that particular energy within this range delta epsilon, okay? So it's a very useful concept because you always want to know how many states are available for the particles to reside in at any given energy. That's a very useful thing to know about. So the next question is, once we know how the total states increases with energy, we like to ask, what are the possible states of the system? What are all the possible states of the system? And so to answer this question, I have to constrain the total energy. And so for this example, for the next few slides in this lecture, I'm going to constrain the total energy so that it's equal to 9 epsilon. My system is going to be this equally spaced set of energy levels. And I'm going to drop in 6 distinguishable particles and just start to ask, what are all the possible microstates of the system that have this total energy of 9 epsilon? So that's the question, the next question. In this slide, I try to enumerate those states, right? So clearly, if I've got 6 particles and I've got a total energy of 9 epsilon, one possible state of the system is I just put one particle in the energy level 9 epsilon. I put the other 5 particles in the 0 energy, and that's one possible state of the system. And in this lecture, I label the states by capital letters, so we'll call that state A. And it turns out there's 6 different ways I can arrange this one particle to be in this energy level 9 epsilon. The next logical state that's accessible would be if instead of having a particle at 9 epsilon, you have a particle at 8 epsilon, plus another particle in the energy state 1 epsilon. The remaining 4 particles would then be in my 0 energy state. This macro state we'll label as capital B, and it turns out the multiplicity of that particular state is 30. So there's 30 different ways I can arrange these 6 particles so that they have this configuration. And it turns out, if you sit down and think about this problem carefully, it turns out there are 26 different states that you can achieve, right? That all have a total energy of 9 epsilon. This chart, this table sort of gives you a visual indication of how the particles are distributed in the different energy levels to achieve this total energy of 9 epsilon. And they also list the multiplicity of each state, right? That's listed on the top value, right? It's kind of important that you know how to calculate the multiplicity of these states. So just to reinforce that concept, I just copy the first three states in the previous slide over here, and I list the number of particles in each state, and then I show you how to calculate the multiplicity of that particular state. Right? So the multiplicity of the state is determined by finding out the number of ways available to put a particle in a given energy state such that the total energy adds up to be 9 epsilon. So this is just the first few entries in the previous table, and it gives you a sense of how these multiplicities are calculated. If you work all this out and you list it in a table, this is the sort of table that you get. These are the so-called macro states. They're labeled A through Z. There's 26 total of them, right? These are the way the particles are distributed in the different energy levels. You'll find that every line in this table adds up to a total energy of 9 epsilon. And then the degeneracy, or the number of microstates for each possible macrostate, right, is also listed. And these degeneracies are something that you should be able to calculate given the fact that this is the distribution of particles to achieve that particular macrostate. It turns out that if you add up all these microstates, you've got 2,002 different ways that you can arrange these 6 particles to be distributed in these equally spaced energy levels such that the total energy of the system is equal to 9 epsilon. So I put this table in the web page, right? You'll be able to download it if you want a hard copy of it, you want to print it off, because we're going to use it in the next few slides to do some useful calculations. And the point I want to make is that once this table is known for a given system, then you can calculate just about anything you want to know about that system. And so the next few slides, I just go through these different calculations to illustrate how you might do a statistical calculation of, let's say, the average number of particles in the second energy level, or what the average occupation number is, how many particles there would be in the second energy level. What's the average energy of if you pulled a particle out of the system, what hundreds of times, right? You prepared hundreds of systems that are identical and you just randomly pulled a particle out. What would be the average energy that you would measure for that particle, right? All that information can be calculated from this table. So I'm not going to discuss the next few slides in any great detail. I'm just going to point out to you that these things can be calculated. They're all calculated based on this table, and I rely on you to spend a few minutes to work through a few examples to convince yourself that all this information that I'm presenting is in fact very easy to get. It's just a question of using the numbers that are available in the system, about the system. So, what type of things might you be interested in knowing? So, in this table, I say, what's the probability of finding one of these 26 macrostates, right? There are 26 macrostates available for the system. What's the probability that if I look at a system in a given instant in time, it's going to be in one of these 26 macrostates? So to be specific, I focus on the macrostate B, and I ask, what's the probability that you find the system in that macrostate B? Well, there's 30 microstates, 30 ways that you can achieve the macrostate B. There's 2,002 total ways that the system can rearrange itself within the constraints of the problem. So the probability that you would find macrostate B is just the ratio of 30 divided by 2,002, and it's about 1.5 times 10 to the minus 2. Right? So this assumes that all these microstates for a given macrostate are equally probable, and that's a very reasonable assumption at this point in the discussion. So you can calculate what's the most probable macrostate that you find in the system. The most probable macrostate you're going to find in the system is going to be the macrostate that has the highest total number of microstates, right? You can ask how many particles exist at a particular energy. So, for instance, on average, of the 6 particles in the system, how many of those particles will have an energy of equal to 2 epsilon? Well, you have to go back to the table, right, the master table. And what you have to do is you have to look at all the states. Let's see, here it is. You have to look at all the states that have particles in the 2 epsilon energy level. You'll see that of those 26 states, about 13 or so have 0 particles in the 2 epsilon energy level. So those states don't contribute to answering this question. Only the states that have an occupation of particles in that 2 epsilon level contribute. Right? So I just worked that case out here. These are the macrostates that have particles in the 2 epsilon level. You have to calculate the ratio of the degeneracy of each state to the total number of particles in that state, right? So that's the 30 over 2002. That's the 120 over 2002. So you have to look up these degeneracies of each of these macrostates. You also have to list how many particles are in the 2 epsilon energy level. So state C has 1 particle in the 2 epsilon level. State K should have 2 particles in the 2 epsilon level, and so on and so forth. Right? You work this out and you find out that on average there's about 0.99 particles which would have an energy of 2 epsilon. So if you just reached in and grabbed out a particle, the average number of particles that you would find in that 2 epsilon state would be very close to 1, about 0.99. And you can repeat this calculation for the other energy states. I just list the results in this table. Here's the 0.989 that we just worked out in detail. You can calculate these would be the number, the occupation number actually. You know, what is the total number of particles in each energy level? And of course, we're going to go from the 0 energy level all the way up to 9 epsilon. That defines our system. What you find is that on average, there's going to be about 2.1 particles in the 0 energy state, about 1.5 particles in the 1 energy state, about 1 particle in the 2 energy state, so on and so forth. If you add up all these probabilities, you ought to get the total number of particles in the system, and in fact, you do. You get 6. You can use these numbers to calculate the total energy of the system. So this is a good check to make sure that your table is complete, that you've considered all possibilities, right? So you can calculate the total energy of the system. It's going to be the average number of particles in each state times the energy of that state. And it's going to consist of 9 terms because we've got 9 states with 6 particles in them. And when you do that, you find out that the total energy is equal to 9 epsilon. And then, of course, once you know that number, you can then ask what's the average energy of a particle in the system. The average energy of the particle in the system is clearly just going to be the total energy divided by the number of particles. So you're going to get like 1.5 epsilon energy per particle on average. So please check 1 or 2 of these entries to make sure you understand how I got it. It's important for you to understand this calculation of probability or occupation number of how many particles are in each energy state. Right? It's important to know how to get that because the next lecture we're going to do that in a little bit more mathematical way. This is more an intuitive approach, and so it's important for you to understand it, to really understand what's going on. The last thing I'll mention is that if you plot these average number of particles in a given energy level versus energy, what you do is you've got you get a curve, you get a chart that looks like this. You can fit that distribution of particles to an exponential, which is what I've done with this solid line. So you can see that these particles are going to distribute themselves in energy exponentially. which is what you would expect based on, let's say, the Boltzmann distribution function, right? So just 6 particles in a system where the total energy of those particles are constrained, right? The statistics of that are well enough defined to start to give you a very good approximation to an exponential fit. So that's kind of useful result of this calculation. So what I like for you to do is I like you to be able to remember and recall the various steps in this lecture. These steps are going to occur over and over again when you confront different problems. And to be helpful here, I've tried to list those 5 steps that we've covered in the lecture, and you should be able to know how to go from one to the other and what it means. The other thing I'll say is that this type of calculation tends to be tedious, right? And you can work it out if you've got, let's say, 10 particles in energy levels that are equally spaced. And if the total constrained energy is something on the order of 10 or 15 energy units, right? You can sit down and in a few hours you can work out all these tables and all these numbers if you understand what's going on. But it's not practical as the systems increase in complexity and as you get more particles present. This approach just isn't going to cut it, right? It's just too detailed. So what we're going to do in the next lecture is we're going to derive a very general statistical distribution law. And we're going to use that law to describe the population of energy levels, right, as a function of energy. And in this more general discussion, we're going to explicitly include the temperature of the system. So in this discussion, we didn't include the temperature T. There's no mention of temperature T in this discussion. All we did is we just said the total energy of the system was constrained. In the next lecture, we're going to do that constraint by specifying the thermodynamic temperature that the particles exist at. So that's going to be the topic of the next lecture. So come on back and listen to that. It's going to be a more formalism approach to thermodynamics, to statistical thermodynamics. We're going to define something called the partition function. We're going to show you how to use it to solve problems in a very simple way. So hope to see you in the next lecture. Thanks for your attention on this one.